We've got a small group here who are looking at research, and we've just completed a 3.3 megawatt solar farm out at Gatton. So I'll try and be brief and give you a quick summary of that, some of the challenges we've faced in getting that up, and some of the research we hope to do. Gatton campus is 80 kilometres west of here. We've recently put 3.3 megawatts. It's connected on the 11 kV grid, and that was one of the big issues for us. Energex were a little bit uncomfortable with connecting at 11 kV. They wanted a 33 kV connection, and you know, I'm well aware that many of you have faced enormous challenges getting connections for small systems. I can tell you it was quite a big challenge to get a connection at 3.3 megawatts. The size of the system, and I won't go to all the details, we've got 5 large subarrays, each on 720 kVA SMA inverters. There are 7,200 First Solar panels on each of those. 3 of those arrays are fixed. 1 is a single-axis array, and 1 is a dual-axis array. There is also another smaller 125 kilowatt array, which is still to be connected. So what we've ended up with is the dual-axis array is quite large and spaced out, and that uses a German-designed Daiger energy tracking system. Each of those has about 45 panels on them. The 3 fixed axes in orange and the single axis in pink. And what that looks like in reality is something like that. So it's quite impressive when you see it. The fixed axis is up here, third one down there. You can see the dual axis over in the distance and the single axis is. So it's quite a nice site. You can drive out there at any time and actually drive around the site. It's not locked off, at least at this stage. So you can get a bit of an idea of what it looks like. That's the fixed axis arrays close up. The panels are all thin film, so they're only 95 watts each with a thin film cadmium telluride. It uses galvanised piers into the ground. I'll show you a few details later on. There's a long beam along here, so each of those is about 200 metres long. And of course, one of the things you have to think about in a design like that is with thermal expansion, that thing can expand by almost 4 inches, 90 millimetres or so. The panels are clipped in, so on. Single-axis arrays are somewhat different. I wish I had a better picture of that actually, but they are laid out in a quite different configuration. It's a fairly cost-effective design as far as it's been engineered for. It hasn't been over-engineered, let's put it that way. I was out there one day in 70-kilometre-hour winds, and we were a bit reluctant to stand downwind of the arrays. They were moving quite a bit, so it's a different ball game. And of course, the dual-axis arrays, which always look the most impressive, and as I said, they're embedded on a large block of concrete, a 340 mil, I think, post out of the ground, and you can see a couple of little sensors on the sides there which detect the sunlight, and they activate the drives to orient both tilt and azimuth to give optimum tracking. The utility concerns, there was a whole list of them, but I'll just focus on 2, voltage regulation and power factor. One of the benefits I was previously the power quality manager at Energex, so I had a bit of an understanding of what their problems were and perhaps some of the weaknesses and the arguments that they might put back. One of the first things we did is we did quite a lot of calculations to look at the expected changes in voltage on the campus for different configurations or different conditions on site, different loads, different generations, different power factors, the sort of things that might bother them. And the reality was that even with solar, there really wasn't much of a change compared to no solar at all. And we were quite confident that even on that piece of rural network, that we didn't think we were going to have too many problems with maintaining the voltage on the network. We had a lot of argy-bargy in those discussions, and I guess one of the take-homes for all of you guys, particularly if you move up into a larger segment of the market, is that we did ultimately agree that we wouldn't raise the voltage by more than about 1%. But before we agreed to that, we got Energex to agree that they would hold the voltage between the blue and the red, which is only about 2.5%. So that was quite an achievement. As you probably realise, across the network, the utilities are allowed in Queensland a 10% variation on the 11 kV, the 11,000 volt network. That's quite a wide range, and they need that wide range, but they don't want to be varying that range at any point on the network. And in fact, they still need to be controlling it fairly tightly at any particular point. So Energex ultimately agreed to hold the voltage within 2.5%. And when we come on, we've agreed not to raise it by any more than 1% above that. These agreements are all on the web, by the way, and we've done that so that people can use them as a precedent. I didn't actually include the link, but if you search my name and connection agreement, I think you'll find it. And the way we've managed that is by using power factor correction. So this is, and I apologise for the technical aspects of this, but for those who are familiar, at high voltages, we consume reactive power. At low voltages, we will produce reactive power and essentially support the network. I guess one of the key things, though, is in the mid-range that we're concerned about, we will try and hold unity power factor. And this is something I think the utilities are moving away from at the moment, which I feel is a mistake. They're starting to create, since earlier this year, the new connection standard in Queensland is trying to drive people for configuring the inverters to 0.9, and I'm sure that a lot of inverter manufacturers will do that by default. I don't believe that's a good thing, because if you consider it, at the same time they've introduced a tariff to charge commercial customers for consuming reactive power. On one hand, they're saying it's bad, we're going to charge you for doing it. On the other hand, they're telling the PV installation industry, it's good, you better do it. You can't have both policies side by side. One of the consequences of consuming reactive power in the inverters is that someone will have to supply it. Someone will have to install capacitors on the substations, or generators will have to run in a fashion that can supply it. That will cost money, and guess who will end up paying for that? The other one was power factor. The studies we did showed that for quite a lot of the time, we would run at power factors well below the 0.9 that's required under the legislation. The legislation does, however, give the utility discretion to allow for lower values. We argued that battle, and we ended up agreeing that they would look at the power factor associated with our generation and the power factor associated with our load as separate things. So we will control both of those within 0.9, even though the total will become quite poor at times. But the fact that it's quite poor is insignificant because it's fairly low magnitudes. Okay, panel failures. One of the things we have suffered on site is we've suffered a number of panel failures. The manufacturer supplies graphs showing the rates of failure over a period of time. That's a 5-year axis on the graph. I can't show you the numbers because they're confidential, unfortunately, but it's interesting to see that over various years of manufacturers, they show increasing failures, which you would expect from any manufacturer. We've suffered quite a few, however, in the first 6 to 8 months of operation, and they're not always easy to see. If you look at that panel there, you can see a very slight deflection there. And in fact, that was the very first panel we realised had failed, and it was picked up by looking along the array and seeing a slightly different reflection in the panels. You really can't see much on that at all, except a slight bit of discoloration at the front. And that's what the back of that panel looks like, and you can see that it's shattered. And we've suffered a number of panels which have completely crazed on the back. We really don't know why at this point in time, but they're being replaced under warranty. Of course, we've also suffered other failures which are a little bit more obvious. I would like to think that that large array out there is serving the purpose of detecting meteorite impacts. I do suspect, though, that it was a stone from a mower. And that's what that looks like close up. One of the things we've done out there, because they're cadmium telluride panels, is before we did anything with that, we sealed it with a spray just to make sure that there wasn't any possibility of leaching. I'm led to believe that there isn't a problem with that, but you know, until you get totally familiar with these things, it doesn't hurt to be a little bit belt and braces. The dual-axis trackers have posed a few challenges. If you look at the picture at the back, you'll see the circle unit is not actually facing the same way as all the others. Those trackers have quite a few cables running up through the mast, and in the middle of that you'll see a limit switch which is designed to actually tell the tracker when it's reached the end of the travel. That particular one's actually installed in the wrong spot. It's actually supposed to be on the outside of that boomerang rather than the inside. But what we did find was happening with them is that all these cables running up through the middle were fouling the limit switch and causing it to stop. And as a result of that, unfortunately, our dual-axis array has been stowed since March and is still waiting remedy. So that has proved an interesting challenge. Another thing that's probably worth noting is that the array out there are all negatively earthed, and unlike the unearthed systems that you're familiar with your transformerless inverters, these larger systems have different configurations. One of the things we particularly insisted upon in our installation was that our inverter be provided with the capability to check the insulation each morning. So that's an AS5033 requirement, which particularly now that the new 5033 only applies up to 240 kilowatts, larger arrays will not have to have that requirement, but we insisted upon it. So each morning the inverter looks at the positive and the negative. If there's any leakage to ground, it says, I'm not going to start off today. Another interesting thing is that some of these larger systems which won't have to comply with 5033 may only tend to use single pole isolators. Now if you think about that, with the negative earthed, if you have a contactor frame, you've now got a potentially live frame if the earth isn't in place. At least if you've got a double pole isolation, you've removed the earth return path on the negative, you've made it a little bit safer. So that was something we insisted upon. One of the other interesting things when you have got a large number of strings in parallel, and we've got 480 strings in parallel on each inverter, is that if you do have a fault to ground, the fuse will blow, but from backfeed from the other strings. And once that fuse is blown, your single string that's faulted continues to feed into a fault. It's not cleared, it stays there. And it's something that people don't expect. Most of us who have gone through the ranks of working with AC circuits and so forth, if there's a fault, you expect it to be cleared. With these systems, they're not cleared, and it will stay there at least until the following day when the inverter checks the insulation. So we've also got some interesting earthing arrangements. You'll see going from clockwise, we have a single earth on the fixed axis arrays. It's coupled to the horizontal beam by some spring locks, which allow for some lateral movement. That is then coupled along the whole array by some beam connectors, which are held in place by self-tapping or self-drilling screws, which are something that in the smaller systems we're certainly discouraged from doing. 5033, in fact, says that that's not to be done. And finally, the tables themselves arrive in a folded fashion, which mean that the cross rails are actually pivoting on a bolt, which is another unusual method of earthing. So it remains to be seen how they handle long term. So research, and this is the final slide, so don't panic. We've got a number of researchers who are looking at different things. We've got Dr. Jan Allam, who's come to us from Wollongong, who's looking at the battery storage capabilities. We've got a 760 kilowatt hour battery arriving shortly, lithium, and he's looking at what we can do in the control functions to mitigate variability of PV and how we can improve the plant utilisation by load shaving. We've got another engineering doctorate, Rufang Yan, who's looking at the impact of large-scale PV integration on networks and looking at developing advanced control methodology for that. And we also have economists working on things as well, and Dr. Phil Wild in the audience is looking at the overall impact of these large-scale PVs on the network. So he's looking at Broken Hill and Ningan's PV farms, which AGL have installed, looking at the impact of that on the national electricity market and looking at how further growth in PV will also affect the market. Okay, thank you very much for that. Appreciate your time.